system identification problems and metrology for quantum microprocessors. Thanks very much.
Okay, thank you, Matt. Okay, so my name is Madalin Guta. I'm from University of Nottingham. My current research is, say, at the overlap between statistics and probability and quantum theory. Yeah, so I've been working on quantum state estimation, on system identification, and on metrology. And my particular point of view is, to try to bring techniques from mathematical statistics into quantum theory. Yeah, so statistics has been developed for, of course, many years. It's a very advanced, mature field, and only a few of these techniques have been actually used in quantum theory. Of course, there is a lot of work done by physicists, but I think there is much more that can be done. So with Luke Boughton, a long time ago in 2007, actually, when I was at Praxis in Sydney, we started to think about system identification in the input-output formalism. And it took a very long time, but now there is a paper on the archive. But in the meantime, that we have done some more work, and this was kind of a bigger thing that was left at the end. So I started to work with him then, and then some of my PhD students got involved in the meantime. I also started to work with Naoki Yamamoto, who is a control theorist, and he will also talk, I think, this week, maybe, later this week, about some work we've done together. And in the meantime, also, I started to collaborate with physicists in Nottingham, Juan Garahan and Igor Lesanovsky, who have a different point of view. They think of input-output systems from a statistical mechanics point of view. So you think of the trajectories as configurations of a statistical mechanics system, yeah, and you want to think to ask questions like, are there phase transitions in such a system, things like that, which I think is very interesting. Okay, so what's the setup? So it's all in the framework that we've been hearing about yesterday and today. So input-output formalism. So there is a system which has some Hamiltonian and some coupling operators to the environment. The environment is seen as an input to the system. So you could have the vacuum. There is an atom sitting in the vacuum, and it interacts with that field in the vacuum. That's the input. And then the atoms, due to the interaction, maybe emits photons. So you can think that the atom scatters this input after the interaction, and that's the output field. Yeah, so it's a kind of scattering problem. Okay, but it's very natural to formulate it like this and to make the connection with engineering, as we've seen. Overall, the whole thing can be thought of as a closed system. So you have a unitary dynamics, and these are described using quantum stochastic calculus. I was tempted to write down here an equation, but I didn't. You have seen many of them already. So in this talk, I will only do things in discrete time, because actually the concepts I'm going to talk about can all be explained in discrete time, and the continuous generalization is only an additional thing. Yeah, it will not add new insight to it. Yeah, but it can be done also in continuous time. Okay, so what's my goal in this kind of research project? Is to have a more comprehensive theory of the output process. Yeah. So in fact, it's not only me who tries to do that. So the whole filtering theory is about, what happens if you measure this output, how do you describe the evolution of the system, and so on. But still, I think there is much more to know about this output as a quantum system. So suppose you don't measure it, you think of it as a quantum system. What kind of properties it has. And there is a lot of stuff that we can learn from quantum information from the theory of matrix product states, with which this is very closely related. So in particular, central limit behavior for fluctuations. So if you look at some kind of additive observables in this output field, do they satisfy central limit behavior? Are the fluctuations of these observables around the mean normally distributed? Also, large deviations As I said before, you can think of the measurement trajectories as being configuration in a configurations of a statistical mechanics system. So you can think of thermodynamics of the trajectories. And then large deviation theory is kind of the mathematical theory underlying statistical mechanics. Yeah, so do they satisfy large deviations? Ergodicity. So there is this question, if I take time average of some measurement, does it converge? If I'm in the stationary situation, does it converge to the stationary mean? Yeah. And other problems in filtering related to the stability of the filtering, purification of a state. So if you observe this measurement outcomes, does the system state purify as you get more and more information about it? Yeah. And also, more recently, I started to think of this setup as a setup for metrology. So suppose that there is a parameter here that you want to estimate. Okay, how can I design the whole dynamics in such a way that I get a lot of information about this parameter? So to use it for metrology purposes. And of course, I guess at some point this could be useful for quantum control, because if we understand this output field, the output field in feedback is supposed to go back into the system, right? So insights into the structure of this output field can be useful for that. Okay, so forgive my simplistic pictures for physical systems, but I want to make a distinction between linear systems. Here you have the input, here you have the output, and this is supposed to be a linear system. These are described by continuous variables, and the dynamics can be described completely on the level of the canonical variables which transform in a linear way. Yeah, and usually if this input is a noise, then everything stays Gaussian, and it's very nice. So there is a system identification theory for a beginning of this, and you'll hear more in the presentation by Naoki. But today I will be talking about nonlinear systems. So nonlinear means basically everything else, like, for example, the atom maser, where you have a two-level atom, you have a cavity, there is the James-Cummings interaction between them. So this is nonlinear, and then the atoms come out either in the ground state or excited state, and you want to estimate maybe some dynamical parameter of this interaction. Yeah? So these are nonlinear systems. Right, so what's the plan? First, I want to say some general stuff about quantum Markov chains. So I said I will be working only in discrete time, but most of the things I'm talking about can be also done in continuous time. Discrete time Markov chains, central limit behavior for time averages. Then I will be talking about the identifiability property. So if I have an unknown parameter, can I identify it or not, or how many parameters can be actually estimated in this setup? What is the precision? So if you can estimate it, then what is the mean square error, let's say? And this is kind of more recent. I'm not sure if I will get here, but can I do better than the standard estimation error, which is 1 over square root of time? Yeah? So there is the so-called Heisenberg limit, 1 over t. Okay. So if you have any questions, please interrupt me. I'm not going to give such a nice historical overview. This is more strictly related to what I'm doing, but I'll try to explain, as well as I can. So in discrete time, the dynamics is quite simple. You have a system, and I will have always finite dimensional systems, okay? And there is a sequence of, say, unit noise, yeah? So if you discretize your time, each of these pieces of time will be one of these noise units, CK, yeah? And these noise units, they move like this, the input, and when they come in front of the system, there is an interaction, there is a unitary that is applied to both of them, and then they move further, yeah? So input, identically prepared states, interaction at the boundary here at the 0 point with the system, and then they move out. Okay, that's the dynamics. So the output will be the atoms, these noise units after the interaction. And because they have interacted with the system, they are not independent anymore. They are correlated with each other and with the system as well. Yeah? So we would like to understand better the structure of this state. In fact, there has been a lot of work on this already. What comes out here from the, say, quantum information perspective is a finitely correlated state. There is this seminal paper about this. It's also very closely related to matrix product states, which you'll see in a moment. And it's also a quantum analog of a classical hidden Markov chain. So in a hidden Markov chain is like you have a system which evolves according to some Markov rule, yeah? But you don't observe this system directly, as in our case, you don't observe the system, you observe the output. So in the classical setup, you have the Markov system, and you observe some kind of signal emitted by this Markov system as it jumps from one state to another. And this signal is somehow correlated with its actual state, but it doesn't tell you where it is. Yeah? So it gives you some information about this. I like to think of it in this way because then you can also take ideas from theory of classical hidden Markov chains. And as I said, so there are standard tools for switching between discrete and continuous time. So you can either discretize time and do this, go into this kind of picture, or go to the continuous limit as we've seen in the talk of John. Right, so what is the output state? Well, first of all, notice that I said there is this unitary, but my assumption is that the input comes in a fixed state. Yeah. So actually, it's not so important what the unitary is, but what's the unitary action on system and the fixed input state. Yeah. So that's an isometry. It's in fact moving. So it shows how the system state, initial state, changes by applying the unitary to its state times the input. Yeah. So this is an isometry. So it's an embedding of the system into system and noise. So system and noise after the interaction. Okay. And this isometry can be written in this way. So it's a sum of some Krauss operators, Ki, times basis vectors in this noise space, in the output space. So what it means is that you can create an excitation I in the output, and when you do that, you apply the Krauss operator Ki to the system. That's one step of the evolution. Yeah? So that's what comes out. System is now in this state, and the output is in this state. But of course, you have a superposition of them because it's quantum mechanics. Now, if you repeat that n times, because the next system comes after the first one, what you need to do is to apply these isometries successively. So this is the isometry corresponding to this one, and then the next one will be this one, and the next one will be this one. Yeah? Which means that you need to apply these Krauss operators, Ki1, Ki2, Kin, like this as a product, and you keep track of their indices in the output. So this was the first excitation you created in the output, and the second, and the nth excitation, right? And this is what you did to the system while those excitations were created. Yeah. Okay, so this is what more or less is called a matrix product state because of this product appearing here. Okay, and this is a pure state of system and output together. Okay, now if you forget about the output and you are interested only in the system, yeah, then that means you trace out the output. Then you end up with the system evolution being described by a transition operator. So you can already see it from here. So in one step of the evolution, you apply this Krauss operator on a vector. So if you think in terms of the density matrices, you need to apply the Krauss operator, sandwich with Krauss operators, the density matrix, and then you add over I because you don't know what I is. That's the measurement in the output. So you average over it. Okay, so this is a transition operator of the system. And if you do n steps of evolution, you just take the power n of this transition operator. So that's the Markov property. Yeah, the system just like a classical Markov chain, you apply the transition operator and you get to the next state. Yeah.
So is it
Yeah.
important for what you say subsequently for the U to remain same from state to state?
Yes, everything will be with a fixed unitary, but of course it's interesting to think of time varying unitary. Yeah. And I don't think there is much done about that. Maybe I'm wrong. Also, that's a good question. Also, why should I have this product input? Yeah, like John said, it would be interesting to understand more general inputs here. They might be outputs from another system. What happens in that case? Yeah. So, okay. So now this transition operator appears here. And it turns out that this is very important. Even if you want to understand the output, this transition operator plays an important role, okay? Especially its spectral properties. So now I'm going to refer back to Michael's talk yesterday. He did a great job at talking about quantum channels. So this is a quantum channel. And there is a kind of general result about spectral properties of completely positive maps. I call it the Perron-Frobenius theorem, quantum Perron-Frobenius theorem, because it's a generalization of the classical Perron-Frobenius theorem for Markov chains. Okay, so what does it say? So if S is an irreducible completely positive map, okay, what does it mean irreducible? It means that I have a system and there is no space that is invariant under this transformation. Yeah. So if there was a subspace that is invariant, that means that the rest is kind of redundant. So then you want to restrict to the smallest bit to understand the dynamics, at least on the smallest bit. Yeah. So irreducibility is a natural concept when you study Markov chains. So if it's irreducible, then the spectral radius is a non-degenerate eigenvalue of S. Okay, so here is the spectrum, and the spectral radius will be the largest, the eigenvalue is the largest absolute value. It's actually also a real and positive eigenvalue. The corresponding eigenvector is strictly positive matrix. Eigenvalues which are on this circle form a group that's related to periodicity. This is in general for a CP map. Now, if your CP map is also trace preserving, so that means it's an actual transition operator of our dynamics, then this spectral radius is actually 1, this number here. And the eigenstate, the corresponding eigenstate, that's the transition, that's the stationary state of the system, and it has full rank. Yeah? So it's strictly positive. Okay. Now, if I also ask that the system is aperiodic, that's what some people call primitive transition operator. So aperiodic basically means that there are no eigenvalues on the unit circle apart from this eigenvalue, the stationary state, eigenvalue 1. Yeah. So all the other eigenvalues have absolute value smaller than 1, and then we have convergence to the stationary state. And essentially the argument is if you take some initial state sigma and you apply this transition operator n times, yeah, and n is large, then because t has one eigenvalue which is 1 and all the others are strictly smaller than 1, when you take powers of t, you will have all the other eigenvalues going to 0, and 1 stays 1, and the corresponding eigenvector is the stationary state, so you converge to the stationary state. Okay, so this is a general result, and what I will use several times is this fact. So suppose I have a little perturbation of the transition operator with some epsilon. Okay, then what happens to the eigenvalues? Well, because it's going to be a primitive transition operator, all the other eigenvalues are, so this one is non-degenerate, the dominant one, and the others have a value smaller than 1. So if I do a small perturbation, the dominant eigenvalue will change smoothly. And there will still be a gap between the dominant and the rest of the eigenvalues. So the gap property will be preserved. Okay, so that means that the asymptotics of such deformed transition operators, they don't even need to be completely positive, will be dominated by their dominant eigenvalue, the one that remains there with the largest absolute value. Yeah, this is the main. It's one of the arguments that is used everywhere. Okay, so let's go back to the picture, the dynamical picture. So suppose that I take this output and now I measure on each of the outcomes, I measure some on each of the output units, a particular observable A. So I get outcome A1, A2, A3, because this was the first that came out. Okay, and the simplest question, because I'm in a kind of stationary regime, I said that in the long time the system goes to the stationary state. What comes in is stationary, so what comes out is also stationary. So in that case, it's natural to think of what happens to the averages of these outcomes, right? So let's take the time average, the sum of the outcomes divided by n. Okay, this has a moment generating function, so its distribution is completely encoded in the moment generating function. And by using the Markov property, it's easy to show that this moment generating function can be kind of collapsed back into the system and expressed in terms of a transition operator. So it's initial state of the system. This is a transition operator, but it depends on this parameter s, and is the power n of that. Yeah. And so what kind of operator is this? It's a deformed. It looks like this. So it's like usual transition operator, but each Krauss operator comes with e to s ai, because I have the expected value of e to s, the sum of the operator of the observables a. Yeah, and ai are the eigenvalues of this observable. So this is CP, but not trace preserving operator. Okay, so the first.
Sorry,
yeah.
Does that mean that the A's are diagonal on some basis? What was
right? So I choose the basis to be the eigenbasis of the observable that I measure, and I write everything in that basis.
Okay.
I can always choose the basis in the output as I like. Yeah, indeed. So these Kraus's are in that particular basis. Yeah.
That's without loss.
Yeah.
So that the moment generating function can be brought back to the system is related to the purity of the whole thing.
It's related to the Markov property. So if you write down what is this expectation, you have to put this matrix product states on both sides of this exponential, and then the matrix structure makes that you can reduce it to this power of the transition operator. And the first theorem is the central limit theorem for such time averages. So first of all, this empirical average converges to the stationary mean. This result was proven in generality in this paper. Okay, but now comes the question. So okay, the average converges to the mean, but what are the fluctuations around this mean? How big are those? Yeah. So you look at the difference between the time average and its expectation. Yeah, so this is still a stochastic thing. It gets smaller and smaller, so you multiply by square root of n, which is its variance, and then it stabilizes and it has a limit Gaussian distribution. Yeah, and of course it's centered and it has a certain variance. Okay, and the variance depends on what observable you are actually measuring. Okay, so the result is that this variance has a concrete explicit expression. And in fact, that you can prove two different expressions for the variance. So the first one is in terms of the transition operator, and you see here something interesting. So it's identity minus T inverse. So this is of the order of the spectral gap of the transition operator. So we said that transition operator has dominant eigenvalue 1, and the next eigenvalue is smaller than 1. So this guy, if you neglect the dominant eigenvalue, this is of the order of the inverse of the gap. So the smaller the gap, the bigger the variance. And that kind of makes sense because when you have small gap, the system is more noisy in some sense, and the variance of things is larger. Okay, so that's the first thing. Another way to express it is this as the second derivative of the dominant eigenvalue of that deformed transition operator. So as I said, this is a deformation of the transition operator. Its eigenvalue is also following, is a function of S. So if you take the second derivative of S equal to 0, you get the variance of this observable.
Sorry, Madalin, can
Yeah.
you expand a little bit on the gap? Because it's the gap of what? Because it's not.
Yes,
system,
so-
right?
So we said that this is the dominant eigenvalue is 1.
Yeah,
right,
I
for
understand
T.
that. I meant it
And
is-
then the next eigenvalue is somewhere here in absolute value. So the gap is this.
Yes, it doesn't just correspond to the system itself, right? It is
It's a property of the system.
of the system.
Yes. Yes. Indeed, that's indeed interesting. It's a property of the system, but A comes in here and in here. So you kind of need to apply this operator to something and then put something at the end and take expectation. Yeah. So A is also involved in the expression of the variance. Yeah. This expression is exactly the variance that you get also if you do such things in classical Markov chains. In fact, if you expand this, this is a sum of t to the power I, and t to the power I kind of tells you what are the correlations between a variable at time 0 and the time I. That's kind of the idea. So let me just say that this is for averages of a single observable measured at each time unit, but you can extend this to functions of several outcomes on several sites, and then average that on time, so sort of running average. Okay, this is done in this recent paper, but that needs a kind of extended deformed transition operator where you take into account not just the evolution of the system, but also this memory, because you want to keep track of these outcomes to take a function of them rather than just one single outcome, several of them. Okay. And also you can do it in continuous time, so then natural thing to look at is counts, total counts from time 0 to time t divided by time, or the integrated homodyne current for the homodyne measurements. And you have a central limit for that. Okay, let me just say quickly what's the idea of the proof. Central limit theorem is always, well, not always, but often proved by showing the convergence of the characteristic function or the moment generating function. And as I said, this can be expressed in terms of this deformed transition operator. And the parameter, the deformation parameter, will be s divided by square root of n because of the central limit behavior that we are looking after. And then what you essentially do is expand in this small parameter s over square root of n. And you can do that directly on the level of the transition operator or on the level of its dominant eigenvalue. So we said that such things, the asymptotic behavior of such powers is given by their dominant eigenvalue. And here we can expand this dominant eigenvalue. The first derivative will be 0, and the second derivative will give you this asymptotic behavior. Yeah? But these two techniques are, one related to, say, Markov processes, and this one is related to large deviation theory. Yeah, so it's kind of connects with different things. Okay, so there is nothing about system identification yet. I just try to understand a bit the structure of the output. So I looked at observables that you can measure in the output and this central limit behavior. So next thing, I'm going to talk about identifiability. So suppose that this unitary interaction, because everything is determined by a unitary, yeah, suppose that this depends on some unknown parameter theta. Okay. And the task is to estimate this parameter by measuring the output state or doing something to the output state. This is not a new problem. In fact, such problems come naturally together with filtering and control problems. Yeah? So already in '96, Mabuchi looked at this, and Weismann and Nollmer and many other people in the quantum control community. And the idea usually is, okay, so if you have an unknown parameter in the system, put it as a coordinate, and just write filtering equation for system parameters plus this new coordinate, which is the unknown parameter. And this works, there's no problem. Or you can use maximum likelihood. That means you look at the data, you compute its probability of seeing such data, and you maximize over this parameter. That's the maximum likelihood estimator. More recently, in the quantum information community, ideas of compressed sensing have appeared, which exploit the fact that this output state is not just an arbitrary state, but is has this special structure of the products of the case. Yeah, so it's a matrix product set. Okay, but none of these methods really looks at the statistical properties of the state. So what is the error of the estimation error, for example, or what's the Fisher information that you get? So that's what we are interested in here. And the first question you can ask is, can this parameter theta be actually identifiable? Do you get some signal out in the output about the parameter theta, or the signal doesn't, you vary the parameter and the signal doesn't change at all, right? The output. And that's the problem of identifiability. So I'm going to say I have two chains. So from now on, everything will be primitive. So irreducible, there is a unique stationary state. I'm in the stationary regime. And I have two of these chains, one which has dynamics given by isometry V1, the other one by isometry V2. So these were like two different unitaries. Yeah? But some part of the unitary is irrelevant, only this isometry part is important. And I call them equivalent if what comes out in both cases is exactly the same quantum state. So the output is exactly the same. Okay. So now the equivalence class theorem is that two chains are equivalent if and only if their cross operators are transformed in this way. So essentially, you take the cross operators of the first one, which live on the system, you rotate them with a unitary, and maybe you multiply with a phase, a unique phase, and then you get the cross operators of the other one. So essentially, this says you can identify everything apart from trivial changes of bases in the system that you cannot see from the outside. If I do a rotation on the system first, and then I do a rotation backwards after the interaction, this will not be visible in the outside world. Yeah? So it's trivial to see that. And the theorem says that those are the only things that cannot be seen. Everything else comes out in the output. Yeah? So that's the main result here. You can also do it in continuous time, and then you have a rotation of the Lindblad of the jump operators, rotation of the Hamiltonian. You can add a constant. This corresponds to this phase here, a constant to the Hamiltonian. Also, what Naoki is going to talk about for linear systems, you can prove such a result for passive linear systems, and it's also an equivalence up to unitary transformations on the system.
So here,
yeah.
Here you have no measurement.
No, right, so that's important. So I'm on a fully quantum level, and I just say, I want the output states to be exactly the same as a quantum state. So whatever measurement I do, I will not distinguish these two systems. And then you find that that's what it means. So the reverse is that if this is not true, there will be a measurement which makes the difference between them. Okay? And again, to prove this is kind of reduces to a semi-group or transition operator. And the idea is, okay, so if you want to know if the two states are the same, you look at the overlap. So here I'm looking at the overlap of system and output. So it's not really, it's a bit cheating, but just for the sake of presentation. So if you look at the overlap between the system and output with dynamics V1, and the overlap between and the system and output with dynamics V2 after n steps, then you actually can reduce it again by using Markov property to a transition operator, which is like the usual transition operator, only that you put cross operators from dynamics 2 on one side and cross operators from dynamic 1 on the other side. Yeah? So this is not a CP map, it's not positive, but it's an operator. Okay? And as we said, you get the power n of this operator, so this will be dominated by its dominant eigenvalue to the power n. right? And
I don't understand that.
Yeah.
Because it's no longer. Well, maybe I'm missing an understanding, but
Yeah.
I thought T is now no longer satisfying your assumptions that showed earlier on that
Yeah.
because it's not a CP map.
yes, it's not a CP map, but still, its behavior is determined by its dominant eigenvalue. So the eigenvalue is largest absolute
It's
value.
going beyond the theorem that you showed earlier.
Indeed, yes, yeah, that's right, yeah. So there are two alternatives. Either this dominant eigenvalue has absolute value 1 or smaller than 1. That's just coming because this is an overlap of two states, so that's always smaller than 1, so the eigenvalue cannot grow, yeah? This quantity cannot grow. And then you can prove that if it's 1, then actually you are in the case of equivalent system and you prove this relation between the cross operators. If it's smaller than 1, it means that you see these two outputs kind of diverge from each other exponentially. Yeah, the overlap goes down exponentially because this eigenvalue is smaller than 1. So therefore, the output states are more and more distinguishable. In fact, exponentially distinguishable in the large time limit. Yeah, and these are non-equivalent systems. This is here, as I said, it's overlap between system and output, but you can actually do it for the output itself. It's the same thing happening. Okay, so that's about identification. Now, what is the estimation precision? So let me just put one slide about quantum statistics because my kind of feeling for this problem comes from state estimation, which is a simpler problem. So let's consider this state estimation problem. So suppose I have a system with a pure state, psi, which depends on the parameter theta in this way. So you take a fixed state psi 0 and you rotate it with a generator with a Hamiltonian g. So e to I theta g. Just take a state and rotate it. Yeah? And I would like to then measure this state psi and estimate theta. Okay, that's a state estimation problem for a very simple family of pure states. And this problem is interesting only, or for me, when you have many samples, because if you have only one system, there is not much information you can get. So suppose that I have n of these states, yeah, an ensemble of identically prepared systems, and then I want to do a measurement. So when I have n systems, typically we know that the uncertainty in estimating the parameter goes down like 1 over square root of n. Okay, so because of that, parameters which are hard to distinguish are at distance 1 over square root of n from each other. Parameters that are far away, they are very easy to distinguish. You can just see it from simple measurements. So this is an argument that in statistics is often used. It's natural to rescale the parameter and think in terms of, in my parameter space, yeah, I have this state psi theta, so I'm going to take a neighborhood in my parameter space of a fixed parameter theta 0, and the size of this neighborhood is 1 over square root of n, and I want to see what happens to the states that are in this neighborhood. So here I have psi theta 0 plus some local parameter u over square root of n, and I have n copies of this. Yeah, and because this is a pure state model, if you have pure state, these are vectors in a Hilbert space. So all the structure of your curve here is essentially encoded in the inner products of the vectors. Yeah? So I take another one, psi theta 0 plus v over square root of n, tensor n. Okay, and the statistical properties would be encoded in this inner product between these two vectors. So now let's see what happens. So I take this inner product. This is tensor product, so it's the inner product of the two vectors to the power n. And because it's just a rotation with this theta, so I get u minus v g over square root of n. Okay, if I take the expected value of g to be 0, that's just a harmless assumption. Then I can expand this in u minus v over square root of n, and I get the variance of g appearing in the exponential here. So just using the fact that 1 minus u minus v squared over 2n is variance to the power n converges to v2 minus u minus v square variance over 2. Right? So in the expansion, this is the first term that appears. Okay, so now this exponential can be rewritten as an inner product of two coherent states. You know that the inner product of coherent states is a Gaussian function. So if I take two coherent states, which are, one of them is localized at square root of f over 2u, and the other one is localized at square root of f over 2v. So one mode coherent states, then the inner product, I'm not sure who is controlling this. This has to go down.
You just got that.
Okay, that's the control. So, so inner products in my initial model, if I take n very large, converge to inner products between a much simpler kind of model, that of a coherent state that I displace with my parameter along the axis q. Yeah. So from here, you know, I kind of understand what's happening. So, for example, how much Fisher information there is in this model for large n? Well, as much as there is in this model, but this model is very simple because I displace a Gaussian state. So the Fisher information is essentially this constant that sits in front of the displacement. Yeah, the more I displace, the more Fisher information I get about the model. And it's equal to the variance of the generator. So that's an important thing for this model. The bigger the variance, the more you rotate the vector, the more Fisher information you get. And it's the derivative of the state squared. Okay, so this kind of argument is not just true for pure states, but can be extended to mixed states as well. And to more parameters than one. So then you will get, when you have more parameters, you will have more of these continuous variable systems and displacements along different directions in that space, but essentially it's the same kind of idea. Okay, so now I want to do this for my Markov model. Okay, so I want to replace this product state, so IID system, this ensemble of identically prepared systems, I want to replace it by the output of my Markov chain. The output is a set of, it's a correlated state, yeah? So it's a different problem, but a similar thing happens. So we go back to our primitive Markov chain. The isometry depends on the parameter theta. I'm going to take the parameter localized around some theta 0 because, as I said, that's where the interesting things happen. That's how you understand statistically the model, by looking in a neighborhood of the size 1 over square root of n. And I'm going to think of this u as being my unknown parameter in that region. And then I look at the overlap because the system and output state is pure state. So I understand it by looking at overlap with two different parameters. So this is system and output state with the isometry with parameter v, and this is the same with parameter u. And the theorem is that, again, it converges to an overlap of two coherent states. So in some sense, in some statistical sense, the output becomes Gaussian. And there is this coefficient f which plays the role of quantum Fisher information of the output. And per sample, so as you run the dynamic, every unit of output that comes out carries an amount f of information. So of course, if you watch this output for a long time, its total Fisher information will be n times f. Yeah, so this is per sample. And the consequence of this is that if you find the best measurement that you can do on the output, you can estimate the parameter theta with variance, so with error, 1 over the Fisher information. So that's in statistics, that's the use of Fisher information. So if you look at an estimator, the mean square error, yeah, goes like 1/n. As you get more and more sample, it goes down. But there is a constant, which is the inverse Fisher information. So the bigger Fisher information, the smaller is the error. And that's the whole game here, is to find this quantum Fisher information. So the best constant that you can get in this setup. Right, so this is an extension of a classical result for hidden Markov chain. So there as well you can show that there is this kind of asymptotic Gaussian behavior of the output, and there is a certain constant that plays the role of Fisher information. Yeah, okay. So the idea of the proof is similar to what we've seen before. You can reduce the overlap to some power of a transition operator. You do some expansion. This is going through the root of the dominant eigenvalue, and you get a second derivative of the dominant eigenvalue as Fisher information. So this is a kind of susceptibility, I guess. And you can also go through the root of more like in Markov theory. That's something that I like very much, and it's an ongoing project. So in the case of the IID states, I said that the Fisher information was the variance of some generator. So I imagine that I rotate my states with a generator G. Yeah? In the Markov case, it's very similar. There is a kind of generator that rotates the output when you change the parameter. Okay, what is this generator? It's essentially this kind of time average. So you take an observable, you evolve it by time I, and then you sum over times. So this is a kind of fluctuation operator, like when you prove central limit theorems. But the question is, what x should you put here to get the Fisher information? And it turns out that the observable that you need to put there is u dot u star. So you differentiate the unitary with the parameter and multiply with u star. And that's kind of natural because in the IID case you have u is e to I theta g, right? So u dot u star is basically ig, right? So that's the same here. But what you need to do is to kind of Markov evolve this operator and take its look at these fluctuations in the Markov regime, and that would be the Fisher information. So because there is not so much time, I will not explain this much more. You can also do the same for the output state itself, which is a mixed state, and it's a bit more complicated. And finally, you can also think of those previous measurements that I talked about. So if I take a time average of some observable, that's the simplest measurement you can ever make, and the simplest statistic that you can choose. What's the behavior of that? And you find that, again, by the central limit theorem, you can estimate the parameter, this local parameter u, because it appears as a mean of the Gaussian in the limit. And you can then compute the Fisher information of that measurement, and you get this kind of ratio. So here is again, the variance appears downstairs that we computed from the central limit, and upstairs is the derivative of the mean with the parameter. So, so you want that the mean of your measurement outcomes varies a lot with the parameter, but you also want that the variance is small. So this ratio appears. This is the signal to noise ratio, essentially, of this statistic. And that's the Fisher information. And of course, the quantum Fisher information is always bigger than this classical Fisher information for that particular measurement. And the open problem is, how big is this gap? What kind of measurements do I need to do? Probably, in general, it's not true that simple measurements will achieve the quantum Fisher information. But on the other hand, the conjecture is that there is some measurement that will achieve it, which is of the type of measuring several of these output units together and then averaging in time. That's kind of my conjecture, and it's it's a part of general central limits here. So the atomizer, we have done lots of calculations for this, and you can plot lots of Fisher information associated with various statistics, like the quantum Fisher information. Fisher information is coming from counting atoms, and you see that sometimes the discrepancy is very large. I discussed about this in praxis a couple of years ago. So having this explicit formula for the Fisher information allows you to basically look at how well you can estimate parameters and maybe choosing the proper measurement to do. So I'll skip the quantum enhanced metrology, and what I want to do in the future is, and maybe if anybody is interested to discuss about this, one of the ongoing projects is to use this stuff in metrology. When the system is at a dynamical phase transition, then it seems that you can estimate parameters with better accuracy. There is the central limit theorem that you can extend further, but I would really like to know if feedback can be combined with system identification to increase the precision, and also whether better input states, how input states can increase the precision in system identification. Right, so sorry for rushing this through the end. Thank you.
Questions for Madalin?
Do you have some information how fast is this central limit approach?
How fast? So I'm not sure what you mean, but so the idea is that you approach the mean, and the fluctuation is 1 over square root of n. Yeah.
Yeah, but this is asymptotic for large n. So what large n means?
Oh, okay. So when does the central limits behavior kick in? Typically, it's very early. So if you throw a coin, that's let's say how many times you need to throw to see the right frequencies. Maybe 50 times or less. Yeah? So central limit behavior usually kicks in very, very quickly, unlike the large deviation behavior, which in theory, it's also an asymptotic behavior, but you need to wait longer. So in statistics, that's why statisticians look at these central limit fluctuations, because you don't need to go with n to infinity. That's definitely
that's assuming uncorrelated.
Well, of course, then that's for IID coins, but of course if the coins are correlated, and in the case of this output, indeed you have correlations, then you have to be more careful. And if you are near this phase transition that I didn't say anything about, that's exactly when the gap goes to 0. There are very long correlations, and then also the central limit takes long to establish. That's true.
So I'm kind of curious whether this type of formalism can then also be applied to the problems in laser cooling, which is the levy flies. So obviously,
well, that's something.
CLT won't hold, but
yeah.
But it strikes me that this sort of concept of looking for the eigenvalue and playing with it is.
Yeah, that would be interesting to look at. So this is central limit, and as I understand, levy flights are a bit outside. Yeah, so.
No, they are, but it's actually a similar quantum problem, in which I've got this sort of atom moving about and light scattering off occasionally.
Yeah.
And then after a very long time, it suddenly finds a similar light spot.
Yeah, but there should be something that is. So it's not exactly in this framework, I guess, if you get these levy flights, because they have.
I don't see a particular reason I can't cast it in terms of a series of quantum systems, each one going by, which corresponds to the possible emission of the spontaneous photon, and the system is now the position of the atom.
Yes. So, for example, I did say it, but all these results are derived for a finite dimensional system. If you go to infinite dimensional systems, so for example, you want to consider the position of an atom, then some of this stuff can be done as well, like we did in the atomizer, but you have to be much more careful, and other things.
So countable infinite is still a problem.
Yes. So there is a so-called compact infinite, which is say effectively finite dimensional, where these things still work, but there is also real infinite, where so things going out to infinity. Yeah, but that's interesting.
So, sorry.
So Andre.
So I was just curious. So you said you actually calculated the Fisher information for if I look at both the system and the output fields, or if I look only at the output fields.
Yeah.
Did you show a plot there? I mean, how different are those things for say,
I
maze
skipped
or-
one slide. They are equal.
Oh.
So the slide that I skipped is this one. So if I only look at the output state itself, which is a mixed state, I can show that in fact that one can also be approximated by the same coherent state, and its Fisher information is the same. And the meaning of this is that the output contains all the information for large n. And that's because of this ergodicity, because of the fact that there is a unique stationary state, and the information flows out in the output. That's an interesting thing.
Okay, one more question.
Yeah, sorry, just a comment on the levy flights. I mean, all practical levy processes are truncated at some level, and truncated levy flights are still the normal central limit theorem. But there's an interesting result where they tend to approach the central limit theorem from the middle of the distribution outwards, and there's a characteristic length scale for that process, which might be interesting. I don't know whether it's the same for quantum systems, where basically the probability mass sort of concentrates in the Gaussian from the center, but it still has very long tails. And it's not clear to me whether you still get that with whether the length scale for that process would be the same in quantum systems.
Yeah, I think that's kind of the question. So yeah, you see all these results that I showed are somehow as time goes to infinity. Yeah, and it might take shorter or much longer time, but somehow that question is ignored. But like what Michael Wolf has looked at, there is also the question, actually, how fast, if you look in time, how close are you to the stationary state? What's the behavior of the evolution? And you can have a very long time staying away from the stationary state and then suddenly going close to it. And
But there are different measures. I've seen different measures of the covariance that look at the covariance of the tails specifically for levy processes. The reason I know about it is because there's a thing called a Kalman-Levy filter, which explicitly used the tail covariance rather than the actual covariance. Because if you look at the second order moment of covariance, it's dominated by the center of that distribution, and you actually lose a lot of information about the tails in that case.
yeah, so I guess this is further refinements of this kind of stuff.
Okay, thank you very much.